SwayamPrabha. Digital India. Educated India.
Good morning students. Today is the second day of our lecture and this is the overview session. And today in the last lecture when I talked about, I told you about 12 world famous designers. I also told you how these designers evolved from the field of architecture towards the field of design, and then later a complete design team that is required to build intelligent systems. Now, in this particular talk and a following talk also, we will give you some example of such intelligent product design. Okay? And the very first in this direction will be in terms of a particular intelligent system called robots. Okay? So, we had a dream long ago that animals, birds and human like creatures will be created by us just like God has created us, and they will follow, these creatures will follow our directions as if we are their gods. This concept is there in the humanity for a very long time. Near about 350 before Christ, Archytas of Tarentum built an automatic dove. This was the sketch that is available today of this automatic dove that can flap in the air and perch from place to place. And though we do not know whether Tarentum was successful about it or not, but actually the design looks something which is feasible, and only question is that how did he power it? We guess that possibly it was powered by compressed air. Compressed air, we should not underestimate the power of it. I will later on talk about at least one system that we are designing today out of compressed air. So, this was the dream more or less of the people as it happened in the beginning. Now, it took more than 1000 years to actually come to some sort of a realistic situation, where around 1495 Leonardo da Vinci exhibited the first mechanical humanoid robot based on cables, pulleys and gears. You can see what goes inside. So, you can see the cables here and you can see the pulleys here. These things are important for us. You keep in mind, we will be later on using all these things, and also we have some sort of a geared system maybe here. Okay. So, all these things together, this system what it would be able to do? Well, it would be able to sit and stand, it will be able to lift its helmet partly, and if needed it will be able to beat the drums. So, clearly Da Vinci had in his mind both entertainment as well as defense. So, that was this sort of system. Then people started to give a name to it. It is called automaton. Automaton is a system which is actually mechanically programmed, and depending on that program, it can do a particular fixed type of movement of some limbs or do some kind of a work, but the entire thing was 100% mechanical. Now, the 18th century beginning, that saw the pinnacle, the peak of this mechanical design, because that was the time when persons like Vaucanson had been able to design a fully functional flute player, and even a very interesting duck which is very famous as Vaucanson's duck, because this automaton, this duck is completely bio inspired. She can splash in pool, she could flap her wings, even if you feed this duck something or grains, it will defecate in the form of silver pellet. So, this was clearly for entertainment. Now, of course, the field did not remain limited towards entertainment, for industrial usage, we have to jump now from the toys and entertainment to manufacturing. But that took maybe around 70 to 80 more years, and 1950, as the automation has steadily progressed with the progress of electric motors and generators, then we started getting newer type of manipulators like Joseph Engelberger, the father of modern robots we call him, developed the robots called Unimet for General Motors. Unimet is used for General Motors, Nokia and Kawasaki for the manufacturing aid. The GM robot could weld and assemble cars at the rate of 110 cars per hour. Great achievement. A human being, you imagine how many human beings would be required to assemble car and then per hour 110 cars. So, it could save lot of manpower. Not only that, this hand later on could also play golf, pour beer and conduct orchestra. So, all through simple hand like manipulators, and this is nothing but an example of a rigid serial manipulator system. Now, from there we go to 1972 to the Waseda University. They are credited, this university in Japan is credited to build world's first modern humanoid robot, and the name of it is called Wabot 2. This robot could walk and communicate with people in Japanese, pick objects from one place and keep it in another place. Later, it also could read and play music. So, that is a Wabot 2 robot, as you can see, playing music. So, this was steadily our improvement towards the development of more and more intelligent system. In that direction, of course, Wabot 2 was not very anthropomorphic, which means was not very human like. A more human like product was Asimo, and Asimo actually means literally dancing humanoid. Honda introduced this robot, and this is famous for its mobility. Asimo can jump the stairs, dance and avoid all obstacles in its path. More importantly, Asimo has a fully functional brain with vision and listening capability, so that it can recognize people and communicate with them. Now, 2006, if we go fast forward, we get a wonderful intelligent system, a robot called Now, which is a generic humanoid which even you can program. We program it in our laboratory. So, Aldebaran Robotics created this Now robot, which is a programmable humanoid robot used for research, and now for the first time computers have a body. You can program Now to walk, talk, perform any complex movements. We have say 25 degrees of freedom at our service, whereas Now has 25 degrees of freedom, and compare it with us, it is about 40 degree of freedom. So, you can say that it is quite versatile in terms of its movement, and today it is available in many countries, helping researchers, helping autistic children and elderly people. So, this is what is the Now. Okay. So, that is another development. 2016, something more human like appeared. This is Sophia. In fact, Sophia is the first robot who got citizenship also of a country. Now, Sophia has much more facial expression than us. Possibly we have about 21 facial expressions, the muscles that move our face, whereas Sophia has about 50 facial expressions. So, that is how it is much more interactive in nature. Now, today there are multiple robots with multiple roles in our society, like this robotic avatar THR3, which is introduced by Toyota. It is used for telepresence. Then the companion and caregiver for children robot called Pepper. It also works as education assistant. Social ambassador robot I told you already, Sophia. Social assistants like Digit as a delivery robot. Then robot actor Robothespian, robotic astronauts like Robonauts from NASA or Vomitra by ISRO. So, there is a whole group of robots for different type of functionalities today. Important thing for us to know is that robots are not the only intelligent autonomous system. IAS, the full form is, keep in mind, because it is related directly to our course, intelligent autonomous system, that is the full form. Okay. So, this is not the type of IAS that you know, right, the not Indian Administrative Service, but intelligent autonomous system. Now, in this category, robots are not the only thing. For example, all the unmanned air vehicle, unmanned ground vehicle, or underwater vehicle, they are all part of this IAS system. Hyperloop, I will show that example, is an autonomous transportation system. Then there is Da Vinci like surgical platforms, that is also an autonomous system. Then we have these autonomous tactical swarm system Atlas, which is used for defense purpose. Then we have AI driven Northrop Grumman X-47B, a completely autonomous aircraft for defense purpose. Play and companionship such as Sony's Aibo, it is an autonomous robot, it is a dog, or Anki's Cosmo. And also we have AI in VR games, virtual reality games like Half-Life Alyx. So, today if you look at it, that these intelligent systems are there in autonomous transportation, are there in healthcare devices, are there in industrial automation, of course, for manufacturing, then autonomous weapon systems for defense and offense, and also for fun and entertainment systems. So, there is a whole range of products where you will need this kind of intelligence to be embedded, and they all come under the gamut of intelligent autonomous system. So, then the very relevant question for our course is that what is intelligence? Okay? How do we define intelligence? Intelligence is the ability to act appropriately, that is important, to act appropriately, where in an uncertain environment, where what is this appropriate action? Appropriate action is that which increases the probability of success. And also, what is success? Success is nothing but the achievement of behavioral goals. So, the more you achieve the behavioral goals, the goals for which a product is designed, the more successful is the product. And the more successful it is, not only in an environment like for which it is generally designed for, but in an environment which is uncertain, right. Like I have this watch here, and if the watch, I know it is designed to work inside this room or inside a normal condition, but if I go deep inside swimming pool, if the watch is still working, because it is not designed for that environment, it is a new environment. So, such uncertain environment, if it still is working when I come out, well, that means this watch is intelligent. So, like that, you have to design systems which can keep itself ready for any uncertain environment. Like we human being, we are designed for certain environment, but you take us to the peak of Everest, we can survive. You take us to the bottom of ocean, we can survive. So, we are intelligent. So, that is what is important, that achievement of the behavioral goals for which a product is designed under uncertain environment is the telltale sign of intelligence, and maximize that probability of success and minimize the probability of failure. That is what is the goal of every designer. Now, in that type of a system, when I define, you would naturally tell me, sir, are there examples of such intelligent system? Well, there are plenty of it. Well, first point is biologically intelligent system, which we will call biological intelligence, abundant all around, right. Need not be just human being, but you think of even a small worm, even a small ant, it is intelligently designed. So, that ant can work in an uncertain unknown environment as well. Then of course, today there is a new kind of intelligence that is coming up, which is taking up major of the job shares of our students. That is what is called computational intelligence, something like artificial neural network or convoluted neural network, which is ruling today's dinosaurs. But of course, they will not become the tomorrow's technology, because there is a limitation, which I will explain to you later on, that the more you increase this computational load on a system, the lesser is the chance you will be able to make it mobile, and hence the lesser will be the chance that it will be utilized for an uncertain environment. So, what is much better than computational intelligence is something which is called embedded intelligence. Work towards this direction has already started last 2 decades. So, embedded intelligence are differ from computational, because it not only relies on computational processing power, but it relies on equipments like microcontrollers, sensors, actuators, and many of its processing activity it does at the sensor end itself. So, it is also known as edge computing, that is, the data is processed locally in the device rather than being sent to a central cloud server, which enables fast decision making. So, embedded intelligence is becoming more popular right now, and however, embedded intelligence is not optimal, in the sense it does not take into account the advantages that you can get from the physicality of an environment. For that kind of intelligence, we would get a new type of intelligence called physical intelligence. So, design principles and mechanisms that allow that leverage from their physical form. You remember in the last class I have talked about a passive walking robot, which has been designed in Stanford. So, this is one which has the physical intelligence, because it can take leverage from the physical form, can take leverage from the material properties and passive dynamics to perform tasks with efficiency, adaptability and minimum computational control. So, that you actually reduce the computational part. So, this is the goal towards which we are progressing. So, we say that from BI, there was a time when there was only BI, then today we are in CI, from CI we will go to EI, and from EI we are rapidly going towards futuristic PIs, physical intelligence. Now, I will give you some examples of such systems, okay. Particularly, I will go up to EI systems. So, one such system that has been developed in our laboratory is called autonomous robot for crop monitoring and localized pest neutralization. So, what does it mean? It means you can see here that these are basically potato field actually. Okay. So, these are potato field in which we have this autonomous robot. What it does is that it monitors the health of these potatoes, the potato plants, and also it finds out that, let us say, there is a specific region where there is some kind of a pest that has appeared. So, you should not apply the pesticides all over the field, because pesticides are carcinogenic. So, it will look into it, its cameras, it will go there, the robot will travel and it will apply specifically the pesticide at that particular point. So, that is the way this system is going to work. So, you can see here that how this system is developed. Okay. So, it has a chassis, for example, which actually has all these manipulator type of things, and then it has adjustable arm configuration. So, that the soil up and down, it has that physical intelligence to take care of it. So, that is where the adjustable arm configuration helps. It has suspension mounts, so that all the vibrations would not affect, and then it has the robotic arms that are attached here that can actually apply. So, this is the robotic arm attached that can apply this particular type of pesticides. So, the range of such a system is designed in a way that it does not go a long distance, but up to 5 km with a speed of about 3 km per hour, lithium ion battery system, temperature range is 20 to 45 degrees. So, it is not very uncertain an environment, and 80 kg is the weight of the system, and it is equipped with cameras like Intel RealSense depth camera. It has Wi-Fi communication and robot operating system. And you can see here that it has acquired the knowledge of different types of diseases of a potato field, like potato early blight, potato late blight, tomato field also, tomato early blight, tomato late blight. It has understood about it, and then it actually works in all these different types of fields and apply the pesticides. So, we will try to see if I can show you some of these videos at this point. Okay, so, these a few of these videos you would be able to see, and you would be able to see that how it is moving and applying such pesticides. Now, I will come to the other variants of such a system. Another variant is something which actually does the plant disease investigator, and it works on the field itself, and it in the field it actually works closer to the ground. So, it has a different type of a movement system, a belt driven system, and its major role is actually to identify these diseases that I have talked about. All these diseases, it takes photograph and it tries to identify this kind of a system and feed that knowledge into this main robot. So, the main robot has to work in addition in tandem with this type of smaller robots which works closer to the ground, because otherwise you will not get such information. And also there is an environmental observator there that actually moves along these lines all over the field and gets the data, different types of data. I will show you what type of data we can record in such a system. So, that is something like you can see that you can record data like light intensity, you can record air temperature, you can record air moisture, soil temperature, soil moisture, as well as the visual images of the system. So, these multiple parameters at different conditions you have to acquire. So, you have to have a multimodal data acquisition system in order to have the embedded intelligence in such a system. So, this is one such example of a project that we have done, which was sponsored by the Department of Science and Technology, okay, at IIT Kanpur. Now, I will talk about another embedded intelligence system. This is the design and development of a substation inspection robot. You can see here this works in an electrical substation unit, and here you can see the kind of a design of the robot, which is based on a rocker bogie mechanism. You can see the pan tilt mechanism here for the camera, the thermal camera, the RGB visual camera unit. So, multiple sensors will be needed for its movement, and with these you can see that this is the prototype of the system in which the driving power is coming from the motors, and it has additional systems like emergency stop system. Then it has the MCB corresponding to it. It has a leader system which actually tells it about the path and the obstructions ahead, and this is the prototype isometric view of such a system that we have developed along with the motor drivers and the power circuit assembly. So, once you have all these sensors in it, like thermal camera, pan tilt zoom camera, and then the Z stereo cam. Thermal camera is required because you need to know in a substation if there is electric insulation failing, then there will be hot spots. So, you need to know about the hot spots. The thermal camera is going to record it. Pan tilt zoom camera is going to record that the different types of dial gauges or different types of areas of failure. Stereo cam is going to record the path, and LiDAR also is going to record the obstacles present in the path, and you also have the microprocessor. This is the brain of the system, which is a NVIDIA Orin system. So, all these systems together create an example of an embedded intelligence. So, you can see that it is in a rocker bogie action against some obstacles like these, and gravel track work, rocker bogie actions, all these different types you are able to see in the test run. Now, one of the intelligence that this system is having is actually object and gauge detection. So, using the artificial intelligence and machine learning, it uses that in order to first of all detect wherever the gauges are, and if there is a gauge there, like let us say this is a gauge, it identifies the type of the gauge, and gauge differentiates between gauge 1, gauge 2s, etc., and then convert this reading, the reading that you can see here, this reading into a digital reading. Okay. So, that is the purpose of it. So, it trained itself using many images, like about close to 5,000 images, and then it is able to detect the objects, detect the gauge, and determine the readings of these analog gauges, and then transfer them into a digital data. So, that is the part, that is the function that it has to work on. Now, I come to the point that these are some of the things that has been already done today. Okay. In this course, we will be precisely able to know that how you will be doing such a thing, but how will the future intelligent autonomous system will be built. So, in order to know that, you have to first see that what goes in an Asimo robot. Like the Honda engineers created the Asimo robot, which has 34 degrees of freedom that help it in work and perform tasks much like a human being, and by using lightweight materials like magnesium alloy structure combined with powerful computers and 34 servo motors throughout its body, it helps the Asimo to move very smoothly. However, if you look at the specification of Asimo, you will understand that what is the energy efficiency of it? It is about 3.23, that is the energetic cost of transport. Compare it with us, which is 0.20, and that famous Cornell biped, which was also very passive, but of course, did not have this kind of functionalities, that was also having very close, that is 0.20. But Asimo, with all the advanced functionalities like us, it is a terrible failure in terms of energy efficiency or efficient utilization of energy, because with this 50 kg weight, it can only run for about 1 hour with a rechargeable 51.8 volt lithium ion battery. So, that is something that we need to avoid in tomorrow's system. How do we do it? How to make IAS energy efficient? Well, one important thing, as I told you in the beginning of the system, that the days of the computational intelligence is really numbered, because you have terrible computational cost, the weight of computer, and then its cooling that you have to give. So, part of the computation has to be morphological computation. That means, the structures and materials will do some of the tasks on its own that will make the life much easier. Okay? I can give you a simple example of it. See, when we walk on any terrain, you really do not always need to watch where you are walking. Your feet itself knows that this is a new surface, and it accordingly adjusts the spread of the fingers, etc., so that essentially you save yourself from those computational tasks, unless that area is very slippery, so that you know now you have to change your configuration from 2 hand to 4 hand or something, I mean hands and legs together. Then or such cases, if you take it apart, most of the usual cases it is the morphological computation that helps us from computational burden. And then the passive dynamics, I told you, leverage from the natural physics of a system, material intelligence, use smart materials, materials with intrinsic properties like shape memory alloy, compliance and adaptability, so that you can incorporate the compliant joints in the system, and bio inspired design above everything, that is take cues, take ideas from nature and implement them in a system. That is what will make the system to be cost efficient. Some examples of such a system is like, I will talk with much more detail in the course, like these muscles that can be simulated using shape memory alloy wires, that is one system, and we have developed it for exosuits and exoskeleton type of works, and where you can get a tremendous amount of weight savings if you use this technology. This is a case where we have used this and compare it with a particular type of actuator called VA4233. And what we have seen, this was the existing design, and it is a motorless and gear trainless actuator if I use the SMA, which is bio inspired, and I will talk about the SMA details later on, like what actually gives this property to the SMA. These details I will talk about at a later time. I am just giving you the overview of it. We have used such SMA wires for this bipennate configuration, and we have used it as an actuator, and you can see that this is what is the bipennate actuator configuration, in which we have utilized such a system first in a 2D that involves so many different types of fields that has to work together in order to create this action, and then this is a 3-dimensional system, okay, complete 3-dimensional system in which we have the bipennate actuation. You see the conceptual visualization of the system to give you an idea of what an intelligent system is, and there is a video there that you would be able to see, and this is how this actuator is moving at this point with a force that you can get, which is greater than 200 Newton. And you see what a tremendous weight savings, 67% with the help of this system, and of course, cost savings by 32%. So, you can further make it spring based in order to make it more efficient. You can also make it hierarchic in order to increase the actuation force further, and of course, you can implement AI based system in order to make it more intelligent in terms of the firing power and both forward and reverse determination of actuation in such a system. Tomorrow's actuators will be built up, robotic links will be built up using such a system. This is just a visualization of the system, and not only you can utilize it for arms, but you can utilize it for buoyancy controlled type of vehicles, and even for the exosuits. So, it has a huge research impact that it will give to us. So, I am just showing you some of these papers and the details that shows about the detail of how we have designed such a system. So, this is where we end today, and in the next lecture I will give you some more overview of the intelligent system design. Thank you.